All right, go ahead and ask questions about your.
Question. What's the upward force?
Yeah.
First off, I did not agree with either of these two. So
Okay, fine. We said it was force applied from the person throwing it up in the air.
Yeah, but there's
no feeler dealer, Jonas.
There's the feeler.
One at a time.
Not there.
The person is not.
Yeah,
No. I want these two groups to discuss it first.
We just said force of gravity downward.
Because
Yeah.
person.
You said force applied because if it was just force of gravity, it wouldn't go up in the air. Like, if it was just force of gravity, there would be no other force pushing it upward.
But isn't it in free fall because it's just a ball in the air?
Well, it's not when it's falling. It's when it's
Yeah, but and technically, if it was being thrown in an arc, it wouldn't even be upward. It would be like diagonally.
What?
It was thrown vertically.
Oh, it was thrown vertically. Oh,
Yeah.
never mind.
Isn't the only force that acts on anything control gravity?
Yes. Well, unless
No, it's
technically
gravity.
air resistance might count here, but in free fall, yeah, only gravity.
So why is
What's the right answer?
Haha, trick question. There is no right answer.
Who's gonna see this?
You?
No, like people that aren't here.
There's no
Like
feeler
other
dealer, Jonas.
Potentially people that aren't here. Maybe the other honors class. They care.
Jonas, this is
Took equal power.
All right, there's a lot of conversing going on. I want to try and focus it. I want to focus it on physics. There were a couple of questions that were asked that were never answered. For instance, what would the feeler dealer be for the upward force? That was the question. Ethan, that's not constructive. If someone feels threatened, they are not going to have the safety to be wrong. I want them to have the safety to be wrong today, because today it doesn't count against you as long as you finish your homework.
I'll leave myself open.
I feel like that's a dad.
I feel open. I'm letting myself open to way too many of these things. I should really stop.
Luke, would you like to respond? You're in the same group. What is the feeler dealer for the upward force?
I think it just depends if you put the person in the schema or not.
If the person's in the schema, would the person be part of the feeler dealer for the upward force?
Yeah, it would be force applied on the ball from the person.
Okay, so as usual with physics, I love physics because we can actually go do it. So if you take this ball and you toss it in the air, and at the peak of its motion, can you explain how you are actually dealing a force to it at the peak of its motion? Go ahead and toss it up. At the peak of at the zenith of its path, the top of its motion, how are you dealing a force to it?
I mean, I see how now it's inertia, but I was thinking that since you apply it from down here, it still acts on it going all the way up.
I agree with you, it's inertia. Can you explain more on that? What do you mean it's just inertia?
Because since it's already in motion.
It wants to stay in motion.
Yes. So the upward force that they were, and again, this happens all the time in our class. Thanks. This happens all the time in our class, is that a person wants to grab at the idea that something is moving. I need a force of motion. I need a force of its energy. I need a force of its inertia, right? And it's not. The inertia is not a force. That's what happens when there is no unbalanced force. Good. I agree. So there should not be an upward arrow on that force diagram on page 1. There's just a single downward arrow of gravity. How about the answer to question number 1? Do your two answers agree?
Yeah, we just
worded it differently.
Okay.
We said the force exerted on the truck by the car is less
We also
than.
put a Y.
Well, if we did put a Y, we would have put because the truck has a greater nose than the car.
Okay. Can you explain your why a little bit, Ethan, for number 1? Yeah, the why.
Oh, okay. I was thinking why, so like axis things. The reason why we think the truck exerts more force is because it has more mass compared to the car.
Okay.
And for all intents and purposes, we kind of just assume that both are going the same speed.
Okay. The speed actually has no effect on the answer, and so that's why it wasn't given, because it doesn't make a difference at all. Zach, I saw your hand first, and then Maggie. Please direct your questions to either one of these two groups.
Well,
same,
On what?
the cars and the truck. This is more.
What's this?
Asking them. How would you like to phrase that as a question?
Can you come back to me?
Sure, Maggie.
Based on Newton's third law, what's the reaction of the third? Why would the force on the truck by the car be greater than or be less than the force exerted on the car by the truck if every action has an equal and opposite reaction?
Because it has a greater mass, so it exerts more force. Because net force equals mass times acceleration. So if it has greater mass, it has greater net force.
Did you hear her question about Newton's third law, though?
Yeah.
So I want you to respond to that part of it. So that part of it, again, is if the truck hits the car and the car hits the truck, why would you not make them equal by Newton's third law?
Because they're not action-reaction pairs.
Okay.
So I was thinking that, like, whenever the truck hits the car is going to go a lot farther than the truck.
Yeah.
So it'll accelerate more. So the low mass is made up by the large acceleration. Does that make sense? I don't know.
So there's 6 people in these 2 groups. Anyone feel free to respond.
First off, that's a lot of like extrapolating for this problem. It's just saying like, let's just say by the time they actually hit, one's gonna have more force than the other. Basically, let's say Diego tried to throw me into the wall. That wall's not going to move anywhere. And also, Mr. Brown did say that for this problem specifically, acceleration didn't really matter too much.
That's not what I said.
Well, like acceleration, well, it never really says.
What do you think, Mr. Brown?
We'd love to hear your opinion.
I mean, it really just
Let's go across the rest of the room. How many of you said they're equal? Okay, 1, 2, 3, 4, 5. How many said truck hits car harder because truck's bigger? That's it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Luke?
No, I said that it's still equal.
11. Okay, 5 to 11. The 5 have it.
No, like I said that.
Oh, you said they're equal. Forgive me. 6 to 10. The 6 have it. The answer is they're equal. And I want to make sure that we do understand this. And so let's spend a minute on this. This is one of those moments during the day when I want you to have a chance to be wrong. And I want your wrong answer to come out now while we are all here. I'm going to try and have this aim at the board. This is not working. Yeah, but I can't switch the camera while it's recording because of this thing. Yeah, I think you should have to hold it for me. How do you hold it for me? Have you hold it for me and aim at the board, and I appreciate you. So really quickly, what I'm going to draw on the board is extremely brief, okay? I'm going to remind us that when you draw a schema for this, we're going to have a truck and we're going to have a car. And these two are going to have a interaction. And I'm going to call this interaction the force of the crash.
Thanks.
No problem. That was so perfectly timed with the word crash, I don't even know what to say.
Wait, I was...
Dahlia took her job a little too seriously, and she's like, not only am I going to hold this,
my
I'm
own
going to provide
pencil
full sound
back
effects for you. I got you covered. I want to remind us that this is the same interaction. Truck, car, car, truck. It's the exact same force. I also want to remind you of where you didn't struggle with this, I think, in the last week, or about a week ago, and that was what if block B was pushing on block A, and there was like a hand that was pushing like this, and block B was actually being pushed by the hand. Let me move this. Yeah, sorry. And these two are accelerating to the right, or have a constant velocity. There was an interaction force of B pushing A and A pushing back on B. They were an action-reaction pair, and they were equal, and that didn't bother you at the time. Do you know why it didn't bother you?
They weren't going against each other.
They are against each other.
So, like,
because we weren't
They're
drawing
going the same
quantitative diagrams?
It's not that it was quantitative. This didn't offend your instincts. Your instinct is this. I've seen car crashes. I've seen movies. I've seen trucks hit cars somewhere in a video, a movie, something. And I know what happens. The effect is the car is destroyed. That takes more force. This is my instinct. But your instinct is not quite correct as far as it takes more force. Maggie was correct, and that the car with less mass, when it gets hit by the force, accelerates much more, and it might have very different damage than the truck with an enormous mass is going to have a very small acceleration. That's what's going on. The forces are equal. You can have a small mass and a big acceleration and equal a bigger mass with a small acceleration when you multiply M and A. Okay? But the forces are the same because the interaction is the same. Let me take it to an extreme, very briefly. What if instead of a small car, the truck hit a bug on the windshield? You ever been driving in the summertime, especially out in the country, and you're driving along and you hear a little whack and you hit a bug? Or you get out of your car and look at the windshield, there's little streaks on the windshield of where you were hitting bugs and you're driving? It happens most often in the summer when there's a lot of bugs out. And so you might imagine that when you smack into that bug, the same question could be asked. Hey, so which force was greater? The truck hitting the bug as it died? The bug hitting the truck as the bug died? Or the two were equal?
Equal.
They're equal. It's the same interaction. Now, the effect on the bug is not the same as the effect on the truck because the bug's very tiny, right? And so the force it takes to kill the bug is the force it takes to do almost no change at all to the truck's momentum or energy or velocity.
So it's like how if we pushed against the wall wouldn't feel, or the wall doesn't.
The wall's not going anywhere, is it?
Yeah.
But the wall does push back equal and opposite because you're in equilibrium, you're not going anywhere. And the wall's not going anywhere. The forces are definitely canceling out. Okay? All right, so that's the first question. And again, 2/3 of you missed that. I'm really glad we vetted that out today. This is one of the most missed areas in the entire year because your intuition tells you when that truck hits that car, look at the effect. How can those two be equal? If a baseball smashes through a window, the window never, ever pushed less than the baseball did, right? And so let me illustrate that briefly. So this is just a little piece of wood, thin piece of wood. And so when a baseball hits a window, the window starts to bend before it breaks. So the window does like this. It bends. The glass actually bends a little bit right where the ball hits it. And I've already shown you how the floor bends when you walk on it, right? By jumping on the floor, and you can feel it. And so is this stick in equilibrium or is it accelerating?
In equilibrium.
It's not going anywhere. What if the baseball hit it harder and it bent more? It was in equilibrium at every moment until it snapped. So here's what I want to suggest to you is happening. Every single moment as I'm bending it and I pause, it's in equilibrium. And that snapped earlier than I wanted it to. The one I had yesterday lasted a lot longer. And when it snaps, it doesn't snap because I push harder than it pushes back. It snaps because it reaches its physical limit of what the material can take before it breaks. So even at the moment where it's breaking, my hands are still pushing equal and opposite. That's why I can feel my hands kind of just, like my hands almost start to accelerate, like there's nothing there anymore to resist because the stick just moves out of the way. So it has an equal and opposite force at every moment until it just can't take it and it breaks. The same is true with a little car when it gets hit by a truck. It gets the exact same force. All right, so I don't want to spend more time on that because that's like one question, but it is a big, important concept in Newton's laws. Thank you, Dahlia.
You're welcome.
Okay, I think we hit 1 and 2. Yes? Let's go to the next page. On the next page, which I don't see that board up. Is that over here? No.
Yes.
Yes, that is yours. That's okay. So it follows a diagonal, and you're saying speeds don't subtract from each other. They are coming at a perpendicular direction, so you get the same speed, and there's no unbalanced force, so it'll continue at a constant v. Okay. Any questions for this group? Again, the first question they said it shoots off a diagonal. Second question, their answer was the same speed. because the speeds don't subtract from each other because they're at a diagonal. And then third, no unbalanced force, so it's got to continue at a constant velocity.
That means after it got hit. Like,
Right, after it got hit. Right, no longer being hit anymore. Right. Questions for this group?
Wait, so what's the path of fall?
Like, just.
The 45 degrees?
Like if
Yes.
you, yeah.
Okay, that's
Yes, Eva?
If the 1D is going this way and it forms a right triangle and you're saying it stays the same, then how is it the hypotenuse? Wouldn't it be more?
Can you read that?
So the V is this value, the V is this value, and then the hypotenuse is this value, and it has to be longer. So how would it, is the value of one side of the triangle the velocity? Because if it is, then the hypotenuse would have to be more.
The value.
Are you saying that the length of the, like, I think we asked Mr. Brown the question that was, is the velocity, like, because the arrows in the problem are longer, but I think he said that the velocity, I think the velocity shooting this way and the velocity shooting this way is the same?
No, we were asking about this, specifically the arrows on the top.
Okay, so you're saying that this is longer than this, right?
Basically, yeah, so if, okay,
That's
if a side, if a side is like based on, if it's like a vector, and if it one side
Connor.
represents the velocity
Okay, yeah, this.
of the ball, then the hypotenuse would have to be more
Yes,
than the velocity.
yes.
Yes.
So what's your question?
Shouldn't it be more?
Your answer is the same, and she's saying, shouldn't it be faster?
So, no, because they're like not subtracting from each other, or they're not adding to each other because they're going in perpendicular directions.
Okay.
Because like,
The triangle thing is confusing.
Can you elaborate on that?
I said
Because-
equal to, I'm just skeptical.
so to add to a speed, you have to go in like this.
Well, actually, not think about
As-
velocity.
Because okay.
As far as we know, it's just like a wall. per se. Like I was thinking about like bowling and like bumpers, kind of like if it hits a bumper, it just bounces right back off because the bumper gives it the same amount of push that it gave. I don't know. You look confused.
Your analogy of a bumper is a really interesting question, but it's not this question. And so a bumper doesn't hit it perpendicular. A bumper doesn't hit it at right angles. A bumper hits it at an angle, which is, does that make sense?
Yeah.
It's different because the bumper hits it a little bit that changes its velocity, but you're right, it could bounce off a bumper and have the exact same speed. That could definitely be true. But this is not a bumper.
Could I say what I, so when I was thinking of solving this problem, I was thinking, so if for this to slow, for the bowling ball to slow down, a force would have to hit it like almost head on. So like either there, or if it would speed up, it would have to hit it from like this side, and that would make it go faster. But since it went in the middle, it just changed direction, but it didn't change speed, I think.
What does other people think? Let's get some other thoughts in this, because all of you did this. If you look at your paper and you're listening to the argument, so it had a velocity and then it got hit perpendicular to the way it's moving, and now it's moving off at an angle. Did it just change direction, or did the velocity, the length of the arrow also change? Did it speed up? Thoughts from those who have not yet shared? Go ahead, Robert.
I believe that they are right, and I agree with them. It only changed direction because what Zachary said is like all I agree with, because with the head on, if you like hit it head on, it will go slower. If you hit it like tail on, it will go faster. But if you hit in like the middle, like it won't go faster or slower. If it's exactly in the middle, it will just like change directions.
Okay. Other thoughts? Anyone disagree? Who says it goes faster? We have a lot of people for equal. Who says it goes faster? Diego, you're not sure? You want to go faster?
For B, yeah, I would go faster.
Why?
Because more force got applied to it, so it has to go faster. Is what's slowing it down if it's frictionless.
I'm going to agree with Zach that it depends on which direction the force is applied. If the force is from behind it, it would speed it up. If the force is from in front of it, it would slow it down. This force is at right angles, though. It's in the middle. It's kind of not ahead, or it's not pushing it forward or backward. So what do you think?
I mean, because like it's a right. I think of it as a hypotenuse, so it's just the two velocities make a right triangle. The hypotenuse is the new velocity.
Class-wide question. Have we ever studied things that moved in 2 dimensions? Have we ever studied things that had a force perpendicular to its direction of motion? Maybe?
Well, technically we've studied
The
things
X
that
and
go
Y
in
axis.
3 directions.
Sure, X, Y, and Z. But we've analyzed, like maybe right before spring break, you had a little quiz over projectiles, right? And what did gravity do to something that was kicked off a cliff horizontally?
It only pulled down.
It pulled down. Okay, did it change the velocity?
No. Yes.
No? Yes?
Actually, yeah.
Vertical, not horizontal.
Technically,
Correct.
It changes the velocity because it changes the direction. So like,
Can you? So we're talking about speed. So let me ask you again, and I'll kind of do it over here on the board. So let's say you have a cliff like this, okay, and Mr. Brown is going to be up here and kick a soccer ball, and soccer ball is going to go like this and land over here.
It's going to have a constant velocity on the x-axis, but a changing velocity on the y-axis.
Okay, so if the velocity on the x-axis is constant, because it's like this direction, I think we agree with that. I've heard that from 4 or 5 of you now. But the force is downward, gravity.
Yeah, so it's accelerating at 9.8.
It's accelerating 9.8 meters per second every second on the vertical axis. So if the velocity, which continues to be tangent to the curve, does this,
So
is the velocity increasing in speed?
Yes.
Yes, it is. And do you remember there was a test question about, can you take the Vx that it started with, it has not changed, can you calculate the new Vy, and can you use Pythagorean theorem to put them together?
Yeah.
Okay, so Eva asked a really good question and then talked herself out of it, which is, if you have a velocity in this direction, and that's your initial velocity, and then you add a new velocity in this direction because it got hit by, I don't know, maybe a hammer. This is a bowling ball, right? So maybe the bowling ball got hit by a hammer, and now you added V2 to it.
Myself out of it, no.
Then the hypotenuse here is clearly longer than both V1 and V2. V1 being, or Vi being the initial speed it had, V2 being the speed that was added to it at right angles, just like gravity affects a projectile at right angles. And the new velocity is clearly longer than the 2 sides of the triangle. It does speed up. I agree with you, Zach. In order for it to slow down, you'd have to hit it back to the left. But it's not being hit to the left. It's being hit in this direction. Go ahead, Zach.
So is it, if you were to measure it at just the VI's perspective, like going to the right, is it going to the right at the same speed, but it's just also going?
Correct.
Oh, okay.
It's going to the right, and the speed to the right has not changed. The number of meters per second it's traveling to the right has not changed. But now it's moving in another direction also. Okay? And so in order to cover both to the right, and in this case this looks like up, but it says this, you're looking down at a bowling ball rolling, so I don't know if it's up or whatever this is, north, south, east, west. Whatever direction this is, it's now moving in 2 directions. Yeah. And so its overall speed is greater.
So the new velocity would be the hypotenuse?
The new velocity would be the hypotenuse. That's right.
Fun.
Yeah. And I also agree with their answer for C, that after it's been hit once with a short, brief hit, it does go in a perfectly straight line and it's not accelerating. This is not a projectile because here gravity continues to pull and toward the ground the entire time it's in the air. That's not what happens to our bowling ball that got a brief hit. Okay? And moved on.
But in that one instance, it's still technically accelerated because.
Can we test
for a brief moment, it was accelerating.
It was a change in velocity and change in not.
Right, which is not the scope of question C. Question C says, after the brief hit's done, what happens to the motion?
Yeah, there's no.
Yeah, then it's in equilibrium. Okay. All right, we still have 20 minutes. We have a long way to go. Let's keep going. Thank you, Dahlia.
Can we test that theory? I want to do. Can I use a bowling ball?
We have a bowling ball. I will let you test it, but not right this second. Okay? But feel free to hang around for a minute after class or whatever.
I have a thing.
Yeah, because I have a bowling ball right over here, and we can test that. Are we on page 3? Let's do page 3. Let's do the force diagrams. So the force diagrams they have over there are good. And I especially like that they have gravity up and they have perpendicular surface force down. There's lots of X's on them. So I'm going to help them out a little bit. And I also have the force diagrams on the board. And so I will kind of take a picture of those a little bit, and you'll have the solutions to this. And so you'll be able to see them there too. And so there it is for the person. There are 4 forces. And this is of, I think the way mine is drawn, the cart's being pushed to the left, which I think might be the exact opposite of what you have in your book. So I apologize, and your homework, so I apologize for that.
Wait.
This is the force diagram for the floor and the earth.
What's force push?
How? What?
Is force push also like force applied?
Mr. Brown, what's force push? Oh, so force push.
Okay, 1 second. I'm now looking at it. I'm trying to figure out if I'm correct that the cart's being pushed to the...
In ours, it's going to the right.
Yeah.
It never
And
says if it's accelerating or it's constant.
I disagree. Yeah, as speeding up directly is implying that, though it doesn't explicitly say, that you're accelerating forward. Yeah.
I'm confused about the floor-earth diagram.
Yeah, good. I'm going to let the group over here comment on it because what they did is correct. Not entirely complete, but it's correct. Why did you... what are you confused about with the floor earth diagram? There's 6 arrows on it.
Okay, wait, so the perpendicular forces are from the person and the cart, correct?
Yes, the 2 forces downward on the floor is because a person and a cart are trying to fall.
Okay.
And they're pushing down on them.
Okay, those I get. Why is gravity up?
Why is gravity up? Why did you put gravity up?
Because we still have, we're pulling the earth up from us as the earth pulls down on us. It's an equal opposite reaction.
Correct.
What?
So like we pull the earth up.
Go ahead.
As the earth pulls down, since that's why we don't go through the earth.
So the interaction on a schema, again, they're correct, between, say, earth and person, okay? That there is a gravitational force down on a person due to the earth, and there's a gravitational force up on the earth due to the person, and those are an action-reaction pair. So mine have 3 red X's on them, okay, because they're an action-reaction pair. And I used a combination of X's and triangles and squares because I didn't want to put 7 X's on an arrow, okay? And there are 7 action-reaction pairs. I'll step out of the way of the board. Go ahead, Zach.
So, does friction make the person go in this?
Mm-hmm. Friction is in the force the person is in the direction the person's actually going. That's right.
So, in your thing, the cart's going to the left.
That's correct. In mine, it's like this little silly drawing down here. The cart and person are going to the left. Yeah. So sorry, some of your horizontal arrows might be flipped. And I did it this way because in a different class, that's the way the group did it. And we started with that, and I just kind of left it on the board.
How does friction make you go?
If the floor is frictionless and icy, then you just slip, and you don't go anywhere. If you try and run.
So then it's not friction.
So then what's not friction?
So then if there's no friction, you can't say that it's a force of friction.
So once again, so if you are on an ice rink and I say sprint and you try and sprint, how well will you sprint? You won't, because you have no friction with which to sprint with. And so right now on this floor or in a shopping cart where you're in a store, when you go to push off, it's you pushing off the floor and your foot doesn't slip out from underneath you because of the traction of your shoe tread on the floor, and that's friction. So friction is what allows all of us to take every step forward. Maggie?
I have like a question.
Yeah.
Does the floor feel like friction?
Yes. That's why you see up here on the force diagram that there is friction on the earth due to the person that is an action-reaction pair with the friction on the person due to the earth. And so literally, have you ever been standing on something, like say a little small rug, and you go to like step and it slips out from underneath you or something, or even a board, or you stepping on a book or a piece of paper, and you go to step and it slips out from underneath you and goes the other way. So yes, whatever you're standing on feels a frictional force equal and opposite.
It goes the opposite.
Yeah.
So how does the fuel dealer? You just messed up my whole perspective of the fuel dealer.
Okay.
Do like anything?
So here I have force of friction and I have PE. And here we have force of friction and we have EP. And so it's the same two letters flipped, and that's why they're an action-reaction pair. So the person feels it due to the earth, and the earth feels it due to the person. And here, just to note once again, the diagram put the floor and the earth in the same object, as this whole laptop's about to go flying on me. So the floor underneath you and the gravitational field of the earth are all being drawn in the same dot because they put the floor and the earth on the same object. And that's just how the review sheet was written, and that's fine. Hey, let me just say one more thing. You will not have any question this hard on the test. This is deliberately a long, involved 3-object. You've done like 5 or 10 problems where there's 2 objects. Expect to see 2 objects on the test. This is 3 objects because I'm quizzing you, I'm reviewing you, I'm seeing do you really know what you're doing. Okay, and is it harder? Yeah, it's harder. Okay, but I like to put things that are a little super hard on the review sheet. I think it's useful for testing how well you understand something. Because if you can do that and you understand that, then the 2 objects is easy. Okay, any more questions on the force diagrams? Yes, Ethan.
So could the force perpendicular and force friction technically be counted as one and the same?
One more time?
So could the force friction and force perpendicular like count as one and the same?
Good question, and we've discussed that before, that when you have a force perpendicular due to the floor, and you have also a frictional force due to the floor of the earth, that you could have a single force due to the surface at an angle in between the two of them, and it might go like that. And we've said that before in class, but we said we don't do that on purpose, because typically the one that's up is equal and opposite to some kind of gravitational field down, and the one that's to the left is usually mathematically treated as an acceleration part of the problem with something to the right. And so for the math reasons, we choose to break the surface force into 2 different pieces, because they're both caused by the surface, but they're caused with a slightly different interaction with the surface. So the reason the floor is holding you up right now is not the same reason it has friction pushing you. Not the same reason. And so we kind of differentiate those 2 reactions a little bit. Okay? Good question. Okay, let's go on. Let's jump into some math.
Wait, what about?
What about?
B and C. Like before.
Yeah, let's do B and C. The force has to be unbalanced in order to accelerate. That's good. So I agree with your answer over there, ladies. How would you, when you say it's unbalanced, can you compare the size of the 2 forces they ask about? They ask about the force you apply to the cart compared to the force the cart exerts on you. And then they ask in the next one in the letter C about the frictional force.
Well, I guess if you there's 2 ways to look at it. You can look at it just between like the hands and the handlebars, which is a perpendicular surface force. That's going to be at equilibrium since you're not pushing through the cart, the cart's pushing on you. But you also have to use the force applied, which is your friction to push the cart forward, like an acceleration. That's how you're speeding it up.
So I'm not sure we directly answered the question again. So if you were to compare the size of the force of the person on the cart, and then look at your paper again and look for the arrow where it's the cart on the person. If you look at those 2 arrows, are they the same size or different sizes? They're the same. Why?
Because they're
Action-reaction pair, and that's correct. So letter B is they should be the same, which is not disagreeing with your answer B. Your answer B says the forces have to be unbalanced in order to accelerate. That's true, but that doesn't answer the question. Yeah. So I agree with your other statement as well, though. Your statement that over here the frictional force of the feet on the person has to be more than the cart pushing back in order to accelerate. Yeah. So there, and once again on the cart is getting pushed in the direction of motion more than friction is working against it to stop it.
Wait, so the friction one, it's that the force of friction on the person is larger.
Then yes, it is.
Okay.
Yeah, in order to cause a overall acceleration, a net acceleration in the system. Yes, the net force has to be non-zero on the system. Yeah. How we doing? Okay, let's keep going. We don't got much time. And since we don't have much time, let's bounce to some harder problems. Who did problem 4 on the not the back page, but the next back page? Who did problem 4? Yes, I know you have that. Anyone else have that?
This one?
Yeah.
Yeah, I did that. Chaz helped me.
No, I'm sorry. Who has it on the board?
We did I can explain it.
Okay. Yeah, if we explain that one, we'll get nothing else done. I think all of you need some help with some of the triangle stuff, though, don't we? Yeah. Let's go right to the back page. Let's go back to right to the back page. Let's take a look at who did 5 and 6 on the back page.
We did 5.
6.
Yeah.
Hey, Miss Brown, are you open in Flex?
I'm not. My advisory is doing their end of the year advisory party. Their seniors, it's our last advisory party ever.
That's really sad.
It's not sad. It's super happy. It's a super happy party. I mean, it's not like I'm never going to see any of them again, and it's not bad. It's just that it's kind of like end of the year party celebrate. So I'm sorry, Flex today's out. B2, I have a meeting. Before, I have one opening at 3 o'clock. Feel free to email me. Not that you're allowed to pull a device out now and do so, because that would be.
Today? Is that today?
Yeah, that was today. Yeah.
Can I get my laptop out already?
No. Good call. Okay, so we're looking at 5 and 6 briefly. We got only 6 minutes. I don't want to waste any time we have. So this group did number 5 with the sled being pulled and got an acceleration of 0.9. Who else did number 5? Okay, over here we have a board with number 5, and we also have an acceleration of 0.9. Okay. Anyone else number 5? Which 5 is this? Oh, this is the child in the wagon. Yes, go ahead. Okay, I say both are correct. So if you need to stand up and move around and take a look at one of these 2 boards, I'm going to let you look at one of these 2 boards for number 5.
4.1 correct?
Yeah, it was. For the last one.
6 is 4.1.
Yeah. Is that what you got?
Yeah.
Yeah. And I'll also take a picture of a few boards here with number 6. So here's 5 again, close up. And 6. And which one do you have? Did you guys do one of the other problems? Or just the first page? Page 5. Yes. Did you show the work for the distance being 50 meters? No, we did not.
Yes. And so you have to find
okay.
the net force. The net force is equal to mass times acceleration. Okay, so the net force going this way.
I got a different time. So I did not agree with this one on 3. My time was double that. So we'll have to look at that in a little bit. Let me see your number 6. So here's another version of number 6, also correct. Looks good. All right, we're going to drop the recording soon. All right, let me... Reagan, if you could hold this angled to the board for a minute, or for... You can sit down. All right, let me make a couple comments.
Yeah.
So you don't really need to do that. You just have to know that they balance out. Unless it says what is the as perpendicular, but you did not find as perpendicular. Yeah, you just use your
Okay. Let me make a couple of comments once again on the strategy of doing this. And what I'm telling you again is in the reading on force diagrams. Let's grab a seat for now. I know you're having good conversations about the forces and the problems, but let's not do that now because we have a few minutes left. So the strategy is to solve a lot of these problems. You have other forces that are going on in this problem that are at angles to the gravitational force. So one of them is the perpendicular surface force, and there's often some kind of force of friction or other thing going on. And you either have to take these two forces that I drew with a blue marker, and you have to break them up into components to figure out what's on the y and the x axis, which we don't usually do because it's just more annoying. And instead what we do is we turn our x and y axis to match those blue forces. Now you don't have to break up the perpendicular surface force to figure out how much is on the y and how much is on the x. All of it's on the y. You don't have to break up friction to figure out how much is on the x and y. It's all on the x. Okay? And so, but now you do have to break up the gravitational force. This one has to be broken up. And you have to break it up into two pieces and figure out how much is on the x and how much is on the y. Because part of this, the part that's going into the hill, is being canceled out by the perpendicular surface force of the hill. They're equal and opposite. Okay? So strategy number one, you tilt your coordinate axes. Strategy number two, you break up the gravitational force into its component pieces. And this angle up at the top of the triangle matches the angle of the hill. We showed earlier why that is. I'm not going to show it again right now. So whatever the force of gravity is times cosine theta equals this side that's adjacent to the angle. And then the opposite side over here is going to be whatever the force of gravity is times sine of the angle theta. So in the case of the skier in number 6, this is what makes them go downhill. The force of gravity in number 6 was 600 newtons, right? The angle was like 35 or something. So what I got for this side right here is I got 344 newtons. And that's 600 times sine 35. So the strategy again, tip the coordinate axes, then make sure that you find the sides of the components of gravity using the angle that's congruent to the hill, okay? And it's 344 down. And we gave you a force of friction of 100 up. So you subtract those two to find the net force, and set it equal to MA. And then you're done. Okay? Okay, tutoring. I'm kind of full for tutoring after school today. I already have 6 people coming. There is a slot left in B4. Other than that, you have 48 hours. I'll put up the solutions to this. I'll put up this video, and I'll link it. And